All right, welcome to Chapter 5, Accumulated Change and the Definite Integral. All right, first section here, 5.1, Distance and Accumulated Change. So a thought experiment, how far did the car go? So here's an example. Suppose a car is moving with increasing velocity and that we measure the car's velocity every 2 seconds, obtaining the data in this table below. So we want to know two things. At least how far has the car traveled, and at most how far has the car traveled. All right. So for at least, we're kind of doing a slightly underestimate. All right. So what we're going to look at is this table of data, right? So for the first 2 seconds, so from 0, there we go. From 0 to 2 seconds, the car travels 20 feet per second, right? So that's 40 feet, etc. And we're going to keep doing this. So for an underestimate, we're going to use the lower number with the higher time on the chart, okay? So that's going to give us an underestimate. So let's calculate that one first. So we'll do, and we're just going to keep doing it like that, right? We're going to multiply these numbers, then add them together. Okay, or no, actually, technically not the 4, 6, and the 8, but it's every 2 seconds, so it'll be times 2 for each one. I'll show you. So here we're going to do 20 times 2, right? So that's for the first 2 seconds, the car went 20 feet per second. Plus, for the next 2 seconds, the car went 30 feet per second. Oops. Times 2. Plus, and we keep doing that, the next 2-second interval, it went 38 feet per second. And the next 2-second interval, it went 44 feet per second. So there's a slightly easier way to do this, right? Since the time intervals are all equal, in other words, they're all 2-second intervals, right? What we can do is, thinking about your algebra, you factor a 2 out of each of these groups of numbers, each of these terms. So we could say this is the same as 2 times 20 plus 30 plus 38 plus 44. Just a little shortcut, but again, that only works if the time intervals are all equal, okay? All right, so punch that into a calculator. You should get 360 feet. So again, this might be an underestimate, or it's an at least, all right, a minimum. And then at most, the second one here, at most, how far has the car traveled? So let me clean this up. All right, and then what we're going to do there is we're going to use the higher number, the next number basically, in the velocity part of the table here. Again, every 2 seconds, okay? So we're going to say at most, this car could have gone up to 30 feet in the first 2 seconds. And we can do the same little trick we did before again, because it's still going to be every 2 seconds, right? So we'll put a 2 out here and then add up all the distances that the car went, or the velocities that the car went in each of those 2 seconds. All right, so we'll do 30, and notice how we're skipping the first one, right? Because that would give us an underestimate. We're going for now an overestimate. So 30 plus 38 plus 44 plus 48 plus 50. And that equals 420 feet. All right, so what we can say is the car went somewhere between 360 and 420 feet in that time period. All right, so again, that's just kind of an over and an under value there. And you'll see how this applies in just a minute here. So visualizing distance on the velocity graph. So we can represent both upper and lower estimates. That's what we just did there, right? An upper and a lower estimate on a graph of the velocity against time. The velocity can be graphed by plotting the data in table 5.1, drawing a curve through the data points. So that's what they did. They used all those coordinate points there, plotted them on this graph, and drew a smooth curve. So this is the curve. All right. Now, look at these rectangles, right? You can see all these rectangles here, 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 right? what those are going to represent, and you'll see in a minute, this is called a left-hand sum, and I'll explain more about that in just a little bit. But a left-hand sum is going to be, well, for an increasing function like this is an increasing function. A left-hand sum is going to be an underestimate, a lower estimate. All right, and so what we're going to calculate is the area of each of these rectangles and add all those areas up, and what you'll actually see is we'll get the same answers. Okay, it's pretty cool stuff. That's how we do it. This is going to lead us into those integrals. Now, if you notice also, so let me clean this up. If you notice also these lighter looking rectangles, so think of them more like this. These are the rectangles, the whole thing. The dark side, the dark part plus the light part, like that. If we add up all these, this would be called a right-hand sum, and this will be an overestimate for an increasing function. Okay, again, adding up the area of all these green rectangles I just drew should give us the 420 feet. Okay, so this is important right here. Shaded area estimates distance traveled, and the velocity is measured every 2 seconds. You can see that right there, those time intervals. Okay? All right, so again, those green ones there are an overestimate because we have an increasing function. And let me see if I can get back the pink. There we go. Pink ones there. I erased some of them, but those are the underestimates. Okay? So you'll see how this applies in just a bit here. So what you notice, though, is with these over and these underestimates, we have some gaps in there, right? So it's an estimate. So for the dark rectangles here, the dark blue ones, notice how we're missing out on these calculations here. We're still missing some of it, right? That's why it's an underestimate. And then for the bigger rectangles, notice how we have this overestimate here, okay? These areas are going to give us an overestimate. Well, you know, there's times, a lot of times actually, no matter what the application, physics, finance, mathematics, etc., engineering and all that, you want to have a much, much more accurate representation or a more accurate area under the curve. So what we can do is, notice how before we measured time every 2 seconds, well, let's shrink that time interval. So how about if we measure every 1/2 second? And then go through the same process. We'll measure every 1/2 second and then calculate the area of all these much thinner rectangles. Now what you notice is for the dark blue rectangles here, you notice now there's a lot less underestimate. And same thing for the bigger rectangles, a lot less overestimate. Okay, so we're going to get a more accurate estimate doing smaller time intervals, right? 1/2 second. Well, we can theoretically keep doing that, right? Well, what if we do every 1/4 second? Then these rectangles are even smaller, and then notice how much smaller these under and over estimates are getting. Okay, so the underestimate, the lower estimate, and the upper estimate are actually getting very, very close together, especially if you notice up here towards the top, there's pretty much nothing to see there as far as over or underestimate. So we could do that to infinity, right? We could make that, we can go to, 1/10 of a second, 1/100th of a second, 1/1,000,000th of a second, etc., and get these really, really, really tiny rectangles, calculate the area, and you can see here, right? If we have so many of those rectangles, we don't even see them anymore, and the lower estimate and the upper estimate are going to be equal. Okay, so that's the general concept of what we're going to do. Okay, now I know you're thinking like, well, how are we going to measure these super tiny rectangles? Well, we're going to give you some skills to overcome that. Okay. All right, so approximating total change from rate of change. Here's an example. So filters at a water treatment plant become less effective over time. The rate at which pollution passes through the filters into a nearby lake is given by the following table. Okay, so there's how many days and the rate in kilograms per day of pollution. Okay, so part A says estimate the total quantity of pollution entering the lake during the 30-day period. All right, so we're going to do the same thing we did before. We're going to find a lower estimate and an upper estimate. All right, so actually, I know it's kind of strange. I should have written this better, but we're actually going to do part B first. Okay, so we're going to do the lower estimate first. And notice again, the intervals are equal here, right? Every 6 days. Okay, so since the intervals of the days are equal, we can just put it out here in front of the parentheses, right? Because in other words, each of those numbers is going to be multiplied by 6 days. All right, and then so we'll use the lower numbers first. We'll start at 7 plus 8 plus 10 plus 13 plus 18. All right, and if you punch that into your calculator, just how I did it there with parentheses and all that, I believe you get 336 kilograms per day. All right, that was the lower estimate. Now let's do the upper estimate. Again, every 6 days, right? But now we're going to start with 8 and move on up. Okay, so 8 plus 10 plus 13 plus 18 plus 35. And punch that in. If I did my numbers correctly, should be 504 kilograms per day. Okay, so again, we have a lower and an upper estimate here. So when the question says estimate the total quantity of pollution entering the lake during the 30-day period, what we're actually going to do is we're just going to take the average of the lower and the upper estimate. Okay, all right, so we take the lower, 336, plus the upper estimate, and divide by 2, right? When you average things, you add them up and divide by the number of items you have. Now, if you punch that into your calculator, make sure you use parentheses appropriately, like I just put in there. And if you calculate this, the answer, should be 420 kilograms per day. Okay, so that's an estimate. All right, so again, if they say estimate, you're going to find the lower and the upper based on the table. Then you're going to average them, add them up, divide by 2. All right. All right, next here. Like I said, we want to improve those estimates, right? Those lower and those upper estimates have a lot of gaps in them, or over and underage. So here's an example. So if T is in hours, since the start of a 20-hour period, a bacteria population increases at a rate given by this function here. F of T equals 3 plus 0.1 T squared, millions of bacteria per hour. So make an underestimate of the total change in the number of bacteria over this period. All right. So we can do it in different ways, right? Just like we did before with the example 2 times ago. We could make the delta T, in other words, the interval of time, 4 hours, right? And you would see we're definitely going to get a pretty significant amount of underestimate. Okay? But we can shrink that delta T to 2 hours, right? And notice this here, where it says n equals 5. That's the number of rectangles or time periods in this case. All right. So if we shrink the delta T to 2 hours, right, over 20 hours, that would give us 10 rectangles, 10 intervals. And you'll see again notice how these underestimates get smaller, or the amount that we're under gets smaller, and we could keep doing it, right? Change delta T to 1 hour. That's going to give us 20 rectangles. Again, a lot less of an underestimate. It's more accurate the more rectangles you create. All right, so right here, more and more accurate estimates of total change from rate of change. In each case, F of T is the rate of change, and the shaded area approximates the total change. The largest n, remember n again is the number of intervals or number of rectangles, and the smallest delta T give the best estimate, right? So this would be the best of these 3 estimates. Okay. And then this is conceptual stuff, just kind of giving you an idea of what we're doing with an integral. All right, so next thing we have are left and right-hand sums. I touched on that just a little bit before. Writing left and right-hand sums using sigma notation. So sigma is this letter right here. It looks like a strange-looking E. It's a Greek letter, sigma. What it means is simply summation. In other words, add it all up. Okay? All right, so I'm going to show you this. Oops. All right, so again, left and right-hand sums. It's just the left and the right refers to of your rectangle, which edge you're using. Okay, so notice here, we're using the point on the curve on the left side of the rectangle. Okay, and of course a right-hand sum. Here's our rectangle. We're using the edge of the on the right side of the rectangle. Okay, and notice how this is a decreasing function, right, in this case. And so a left-hand sum is an over estimate, because you see we have those areas that are above the curve. And for a decreasing function, right-hand sum is an under estimate, so be careful with that. Okay, all right, so this is the symbolism here. All right, so this is, I know this is a big mess right here, but I'll explain it. So again, you see this letter, sigma, it means add them all up. So what we're going to do here is, oh, and then it tells you the intervals, right? So it's from I equals 1 to n. Okay, and they'll give you these numbers. You'll see in just a little bit. I'll show you some examples. But f of t is the function value, and delta t is the interval, right? So your time interval or your x value interval. And that's what we did before, right? We took the function value times the delta t plus the next function value times delta t, and we kept doing that until we got to the end of the data. That's what they're showing you here, right? And left-hand sum means the same thing. You're just starting at a different starting point, okay? All right. So that's section 5.1. So now 5.2. So now we're going to see what those left and right-hand sums will do for us. All right, they're going to help us get better at estimating the area under the curve. All right, so section 5.2, the definite integral. Taking the limit to obtain the definite integral. All right, so there's a lot of mathematical jargon here. I'll explain it as best as I can. So here, suppose f, so suppose your function is continuous for t between a and b, right? So in other words, think of these as x values, right? A, t, and b are all x values. They're on your horizontal axis. So t is somewhere between a and b, and of course this notation means it could include a or b. Then the definite integral of your function from a to b, written like this. So this is the notation. Here's how we state this, okay, in words. It's the integral from a to b. Now, I know it's weird, but we're going from bottom to top. So the integral from a to b of your function in terms of the variable t. Okay, that's how we say this. Let me say it again. The integral from a to b of the function in terms of t. Okay? Again, that's just the fancy mathematics behind saying find the area under the curve, right? And the curve is the function. Let's see. So this is the limit of the left-hand or right-hand sums with n subdivisions, right? So again, n is the number of rectangles or number of intervals on your x-axis, as n gets arbitrarily large. In other words, goes to infinity. In other words, just gets so big, we won't even be able to see the rectangles anymore. They're going to be so thin. In other words, if these t values, just notation for different t values or x values, are the endpoints of the subdivisions, all right? All right, then the integral from a to b of f of t dt equals the limit as n approaches infinity of the left-hand sum, okay? And this is more of the notation-wise of what I just said. And same thing here, the integral from a to b of f of t dt equals the limit as n approaches infinity of the right-hand sum. And this limit as n approaches infinity thing, again, it just means we're going to keep shrinking the number of, the interval of rectangles. In other words, increasing the number of rectangles getting close to infinity. Okay, that's what that notation means. So each of these sums is what's known as a Riemann sum, or it depends who you ask. It could be called a Riemann sum. I don't know. I say Riemann, but who knows? I could be wrong. F is called the integrand, and A and B are called the limits of integration. All right, so just some terminology for you. Make sure you know that. Okay. All right, so again, this whole thing is called the Riemann sum. Your function is the integrand, and these little guys here, A and B, are the limits of integration. All right, so here we go. Estimating a definite integral from a table. So actually, we're going to do that same thing we did before, the lower and the upper sums, or estimates, either way, same thing. So the values for a function f of t are in the following table. Estimate, and again, we're going to say this properly, right? Estimate the integral from 20 to 30 of the function in terms of t. Okay, so here, let's do the lower estimate. All right, and notice this is an increasing function, right? The y values, f of t, are getting bigger. So this is an increasing function. So a lower estimate would be our left-hand sum, also known as LHS. Okay, so if you see that, LHS means left-hand sum. So we're going to do what we did before. So we're going to do, now notice the time intervals are all 2, right? Right, so that delta t that they're asking you about right here, delta t is 2. So we're going to put that here. All right, and then for the lower estimate, we're going to add up the first 1, 2, 3, 4, 5. These 5 y values. Okay, so let me write it in function notation first, then I'll put the values in. So, oops. So it's f of 20. Oops. That's a plus sign. Plus f of 22, plus f of 24, plus f of 26, plus f of 28. And we know what those values are because they're in the table. So in other words, it's 2 times 5 plus 7 plus 11 plus 18 plus 29. Punch that into a calculator, and you should get 140. Okay, so that's our lower estimate, our left-hand sum. So now let's do the upper estimate. And again, since this is an increasing function, the upper estimate is going to be the right-hand sum, RHS, right-hand sum. Same process, but we start with the second one here, right? Should clean that up. There we go. Yeah, so we're still using intervals of 2 seconds. That's the delta t. All right, and then we're going to start at f of 22, though. So f of 22, f of 24, plus f of 20, oops, not 25, f of 26, plus f of 28, plus f of 30. Plug in the numbers. All right, so we're going to do 7 plus 11 plus 18 plus 29 plus 45. And punch that into a calculator. Again, just as I did there, you should get 220. Okay. So now, to estimate this integral, this definite integral. So definite integral means we know these limits of integration. They're given to us. Okay. So in other words, estimate of the integral from 20 to 30 of f of t dt equals the average of these lower and upper estimates. So 140 plus 220 divided by 2, which gives us 180. Okay, so that's how we're going to estimate these definite integrals. All right. Next example, so more kind of touching on terminology here. In problems 1 and 2, rectangles have been drawn to approximate the integral from 0 to 6 of g of x dx. Okay? All right, so look at these graphs. So we're looking at this graph here. So do the rectangles represent a left or a right sum? So be careful. It's where the corner of the rectangle touches the curve. So notice for each rectangle, it's the right side of the rectangle, right? So this is a right-hand sum. In this case, do the rectangles lead to an upper or a lower estimate? Well, this is an increasing function, right? The y values are getting bigger. And we have a right-hand sum, so notice we have overage, right? So this would be an upper estimate. All right, what is the value of n? Remember, n is the number of rectangles or number of intervals on the x-axis. Either way, we can see we have 3 rectangles there. 1, 2, 3. All right, and what is the value of delta x? Let me clean this up. There we go. The value of delta x is simply, this is kind of a mathematical way to do it. Notice our highest x value here on the graph is 6, and we have an n value of 3. So delta x equals 6 divided by 3, right, which equals 2. Okay? All right, so again, this little delta x formula equals, you basically think about it, the highest x value divided by n. Okay? All right. Another example down here. It's actually the same curve, right? But this time we can clearly see we have a left-hand sum, right? Left-hand sum because the left side of each of the rectangles is touching the curve. So in this case, do the rectangles lead to an upper or a lower estimate? So we have underage here, right? In other words, we're missing some of the value here. So that's a lower estimate. What is the value of n? Well, again, there's 3 rectangles. And what is the value of delta x? Same as before, but right, we'll show some work. So delta x equals 6 divided by 3, which equals 2. Okay? All right, so there's some work on terminology. Let's see, section 5.3, the definite integral as area. All right, so when f of x is positive and a is less than b, right? So in other words, when you have your function above the x-axis, that's what this part means. When f of x is positive, it means your curve, your graph, your function is above the x-axis. In other words, it gives you positive y values. That's what they're referring to here, positive y values. And a is less than b. So remember, a and b are x values. So in other words, a is on the left and b is on the right. That's what that means right there. Okay, when you have that situation, the area under the graph of your function between a and b equals this definite integral. So let's read the definite integral again. So again, it's the integral from a to b of f of x in terms of x. Okay? So the area under the graph equals the definite integral. That's very important. Remember that. The area under the graph equals the definite integral. All right? And so just some little graphical examples here. What we could do, so you notice the delta x is a little bit smaller there. And again, what we want to do is make more and more rectangles. In other words, make delta x smaller and smaller. And if you do that, you get the definite integral. All right, so the shaded area equals the definite integral. Again, very, very important concept. All right. All right. So here, this is important as well. When f of x is positive, again, that just means your curve is above the x-axis. For some x values, and negative for others. Okay, so negative means under the x-axis. Okay, so again, f of x is positive above x-axis and negative below the x-axis. Okay, that's very important. And again, a is less than b, which again means a is on the left and b is on the right on the x-axis. Then the definite integral from a to b of f of x dx is the sum of the areas between a and b above the x-axis counted positively, and the areas between a and b below the x-axis counted negatively. All right? In other words, that's what they're showing you here. So this first example here, example A, is, well, we see the whole curve is above the axis, the x-axis, right? So if you calculate that area, they're saying the area equals 8 units, okay? This one here, now notice this curve is below the x-axis. So it says area equals 6, but we would count that as a negative 6 because it's below the x-axis. All right, so now we have one that kind of incorporates both. All right, so the area of this part of the curve is positive 10 because it's above the x-axis, and the area of this part here is negative 3. All right, so in other words, if we want the total area of f of x here from 0 to 5, in other words, the integral from 0 to 5 of f of x dx, we would do the positive 10 minus the 3, which equals 7. Okay? And we should write it out like that for the others. So in this case, the integral from 0 to 5 of f of x dx equals negative 6. And then for this one here, part A, the integral from 0 to 5 f of x dx equals positive 8. Okay? All right. Let's see. Now the area between two curves. All right. So I know the notation is kind of heavy here, but again, I'm going to explain it. So let's look at it graphically first. What we want to find is this blue shaded area, knowing we have f of x right here and g of x right here. Okay. So if you remember back to your algebra days, algebra and pre-calculus, if you took pre-calculus, it's kind of like, remember that, you have a rectangular pool with a walkway around it, right? So here's the water, here's the walkway around it. To find the area of the walkway, you would take the area of the outer rectangle and subtract the area of the inner. Do you remember that? Hopefully. I wish I could see your faces, but hopefully you remember that from back in algebra. It's the same concept here. There we go. We're going to take the area under f of x, which is all of this, right? And we're going to subtract the area under g of x, which is this part, which will leave us with the area between the two curves. That's what all this crazy notation is here. So let me explain it though. All right, if f and g are continuous functions, remember continuous means we can draw them without lifting our pencils, right? Or stylus or whatever you're using here. Clean that up, there we go. All right, so f and g are continuous functions. And g of x is less than or equal to f of x for x between a and b. In other words, fancy way of saying the g curve is always below the f curve, right? It's never going to cross through it or become above it, okay? At least on this interval of x values, okay? Then the area between those two graphs is this right here, all right? So just like I said before, it's similar to the algebra problem of finding the area of the walkway, the outer part. We take the curve that's above, find its integral, or its area, minus the area of the curve below it. And then we get that area in between. Okay? All right, so let's do an example of this. So actually, A and B are the same. They are the same. So we're just going to do part A, but it's all the same. And I'm going to teach you how to do this on your calculator. So when they say find the total area between this function, in other words, we're taking the x cubed function minus the x function, and the x-axis for x between 0 and 3. Okay? So what they're saying is we want that area between the two curves. So here's just a rough sketch of this. So here's the x cubed up to 3, and then minus the x graph. So that's that's x cubed minus, oh, there we go, minus x. Again, this is a very rough sketch. This is x, so we want this area between. Okay. All right. Oops. No, I did draw that wrong. It would be more like that. There we go. That's x. Okay, so in other words, we want this area in between. All right, like we said, so we're going to take the curve that's above, in this case the x cubed, the area under that curve minus the area under the x curve between 0 and 3. In other words, that's what we're finding, the integral from 0 to 3 of f of x dx. F of x is these two functions combined. All right, so to do that, so let me clean this up so I can write out some directions for you. Okay, so on your calculators, hopefully you have a TI 83 or 84. If not, that's okay. There are websites and all that. You can just simply Google integral calculator. So Google, integral calculator. Right. One of the websites a lot of people use is Wolfram Alpha. .com. Either way, you do it. So I'm going to show you how to do it on the TI 83, 84. You're going to hit the math button, which is on the left side, left edge there. When you hit math, you'll see a screen come up. Now you're going to arrow down to option number 9, which it may not be 9 on everyone's, most it should be, but it'll say FNINT and then parentheses. Okay, in other words, that's function integral. Right, so you hit that, you hit enter. Oops. And then you'll see it come up, right? It'll allow you to type it in. What in the world is going on with my stuff here? Okay. We're going to type it in. So it's the integral from 0 to 3, right? There's our x values of the function. So in parentheses, x cubed minus x dx. Okay. And it should come out to 15.75. All right. If not, please contact me, of course. And I can give you some pointers on that. All right, so that's how we're going to do those. All right, so we're on to section 5.4 now, interpretations of this definite integral. Notation and units for the definite integral. So the unit of measurement for the integral from a to b of f of x dx is the product of the units for f of x and the units for x. Remember, product means multiply. All right, so here's an example. If R of t represents the rate at which the heart is pumping blood in liters per second, and t is time in seconds, give the units and the meaning of the following integral. All right, so the meaning of this integral is the integral represents the total amount of blood in liters pumped by the heart from t equals 0 to t equals 10. Time equals 0 to 10 seconds. All right. All right, so the way they got liters, right, is again the product of f of x, of the units of f of x times the product, times the units for x. In other words, we're doing liters per second times seconds. Well, seconds divided by seconds, we get liters. Okay? That's how they got liters. All right. So if f of t is a rate of change of a quantity, then the integral from a to b of f of t dt equals the total change in quantity from time equals a to time equals b. Okay? All right. So here's a quick example. A man starts 50 miles away from home and takes a trip in his car. So he moves on a straight line, and his home lies on this line. So his velocity is given here. So we're giving you this graph. So I should have cleaned that up. Sorry. All right, so when is the man closest to his home? So what we're going to notice before we're going to talk about what we talked about before. So the area of the curve above the x-axis, so here's the x-axis, is going to be positive. Okay? All right, so when is the man closest to home? So he's moving towards home for these first 2 hours. All right? So notice, and then they're going to tell you the area of this curve. We have to tell you this. There's no way to calculate it right here. The area under this curve is 30. All right? So he's closest to home after 2 hours because he's moving towards his home for those 2 hours. Approximately how far away is he? Well, he started 50 miles away, and he got 30 miles closer. Right? So 50 minus 30 equals 20 miles from home. All right, and then when is he the furthest from home? Well, for the next 3 hours, he's traveling away from home. All right, and the area under this curve is 105. So he's 20 miles from home after 2 hours, plus 105 miles away from home after the next 3 hours. So he's a total of 125 miles from home. Okay, so that's illustrating, the area of the curve above the x-axis is positive, area of the curve under the x-axis is negative. All right, we can apply this to the bioavailability of drugs as well. So example, concentration curves for a drug administered by 2 methods are shown in this graph below. Describe the differences and similarities between the 2 administration methods in terms of peak concentration, speed of absorption, and total exposure. All right. So here we go. There's the answer. So we'll talk about these. So method A has a peak concentration more than twice as high that of method B, right? So peak concentration just means maximum Y value. Because method A achieves peak concentration sooner than method B, that means the drug is absorbed into the body more rapidly than B. Okay? And we can see that because the curve skyrockets here for A, but kind of takes its time for B to get to the max. Finally, method A provides greater total exposure to the drug since the area under the graph of the concentration for method A is greater than the area under the graph for method B. And that would be something if you had, specific functions, specific equations for these graphs, you'd be able to calculate that on your calculator. Okay? All right, so just some differences there. All right, sorry, I gotta clean this up. All right. So the next one here. So section 5.5, the total change and the fundamental theorem of calculus. All right, so the fundamental theorem of calculus. So capital F prime of x, in other words, the derivative, is continuous for x between a and b. All right. Again, that just means you can draw that function without lifting your pencil. So then we get this. The integral from a to b of f prime of x dx equals f of b minus f of a. Okay? In words, the definite integral is the derivative the definite integral of the derivative of a function gives total change in the function. Okay, so here's an example real quick here. The graph of a derivative f prime of x is shown. So this is your derivative graph, not your function, so be careful. This is the derivative. So fill in the values of the table for f of x. So we're using the derivative to figure out function values. Be careful with terminology. Okay, so let's calculate this stuff out. All right, so remember the derivative, the area under the derivative curve means the rate of change, how much it's changed. So what we're going to do is we're going to calculate the areas. We're going to make a bunch of shapes here and calculate the areas. Okay, so notice we have some triangles here, we have some rectangles here, right? Okay, so let's calculate the area. So we know, let's see, so area of a triangle, so remember that is 1/2 base times height, which in this case we're going to say 1/2 the x value times the y value. Okay, so look at this first one here, this first triangle. The base is 1 unit, right? It says 1 unit right there. I kind of drew over it, but you see it. 1 unit, and the height is 1 unit, right? So 1 times 1 is 1. Half of 1 is 1/2, right? So this is 0.5, but remember it's under the x-axis, so it's negative. Okay, so let's calculate all these areas first, then we'll apply them to the graph. So we actually know this triangle is the same, right? It's 1 unit by 1 unit, and half of that is, again, 0.5, but negative since it's below the x-axis. Now these two rectangles here, the area of a rectangle is just simply base times height. Well, we know this is 1 unit, this is 1 unit, so these are 1. Well, -1 for each, right, because they're below the x-axis. Now this triangle here, same thing, 1 by 1 times 1/2 is 0.5, but that's positive because it's above the x-axis. And this rectangle here is 1 by 1, so the area is 1. Okay, so what we're going to do for each of these intervals on the graph now, on the table, is we're going to take the f value, the function value, and we're going to add the area of each of these rectangles as we go on each delta x. In other words, each interval on the x-axis. In other words, to find, why does it do that? All right, so to find the f of x value for x equals 1, we'll do 2 minus 0.5, right? Adding a negative just means subtract. So that gives us 1.5. So that was going from here to here. Now to go to this one, we go to the next rectangle on the graph, which is -1. So 1.5 minus 1 is 0.5. Next rectangle was -1, right? So go to here is 0.5 minus 1. Be careful with your signs here. 0.5 minus 1 is -0.5. Okay. Next interval, we are going to subtract 0.5, so be careful. We're at -0.5 minus 0.5, which is -1. Okay, be careful. All right, and then the next interval, we have a positive 0.5, so -1 plus 0.5 is -0.5. And the last rectangle says add 1. So -0.5 plus 1 is positive 0.5. Okay? All right, and there we go. That's how we figure these type of problems out. All right, let's see. Next thing we have here is marginal cost and change in total cost. Okay, so notation here, C prime of Q. Right, so that means the derivative of the cost function for a certain quantity, is the marginal cost function, and C of 0 is the fixed cost. In other words, the cost of producing 0 items. So cost to increase production from A units to B units, C of B minus C of A, which simply means that definition we talked about before. We're going to take the integral from A to B of the marginal cost equation. All right, total variable cost to produce B units is that same, or is the interval from 0 to B of the marginal cost equation. And the total cost of producing B units is the fixed cost plus total variable cost. In other words, those two things right there. Okay, so that equation there. All right, so let's look at this one here. All right, so the marginal cost, C prime of Q in dollars per unit, of producing Q units is given by the following table. So there's all your data. All right, so they're saying part A here, if fixed cost is 10,000, that means, in other words, C of 0 equals 10,000. Estimate the total cost of producing 400 units. In other words, Q equals 400. All right, so we're going to use what we learned up above there. So estimated cost is going to be now the integral from 0 to 400, right, of C prime Q dq. Okay, which what we figured out before, the way to figure that out is we're going to do the left-hand sum plus the right-hand sum and divide by 2. So we got to figure out the left-hand sum and the right-hand sum. So here we go first. Left-hand sum. So notice the Q intervals are 100, right? The delta Q. So 100 times. And what we're going to do is add up the first 4 here, because 0 to 400, right? So 1, 2, 3, 4, right? So 4 intervals. So, oh man. All right, let's see, 25 plus 20 plus 18 plus 22 equals 8,500. And then the right-hand sum. Again, the intervals, the delta Q is still 100. But now we're going to start with the higher numbers, right? So 20, man, my pen is a mess today. 20 plus 18 plus 22 plus 28, and that equals 8,800. So we'll take these two numbers, plug into the right-hand and left-hand sum here. So we get 8,500 plus 8,800 over 2, which gives us $8,650. Okay. All right. Part B here, how much would the total cost increase if production were increased 1 unit to 401 units? Well, that's what the chart is telling us right here. Let me clean this up so we can see better. They're saying for 400 to 500 units, the change is 28, right? So in other words, C prime of 400, the marginal cost at 400 equals, or actually, I'm sorry, in this case, sorry, there we go, 401 is $28. Okay? All right. And we're almost done here. Section 5.6, the average value. So the definite integral as an average. So average, again, you add up and divide, right? So it's kind of the same thing what we're doing here. So we're going to do 1 over b minus a. Remember, a and b are x values. These same as the limits of integration that you're going to use. So we'll do 1 over b minus a times the integral from a to b of f of x dx. Okay, that's what they're showing you here. So visualize the average on a graph. The definition of average value tells us that the average value of f times b minus a equals the integral from a to b of f of x dx. So let's interpret the integral as the area under the graph of f, right? We've done that before. If f of x is positive, again, if your function is above the x-axis, then the average value of f is the height of the rectangle whose base is b minus a. All right, so in other words, just find the find the area of that rectangle as they drew there, the black one, and whose area is the same as the area between the graph of f and the x-axis. Okay. All right, so here's a quick example. All right, so the population of McAllen, Texas can be modeled by this function here, where P is in thousands of people and T is in years since 2000. So use this function to predict the average population of McAllen between the years 2020 and 2040. All right, so this is how we're going to do it. So we're going to say, so T equals 20 to T equals 40, right? Years from 2000, right? So T is in years since 2000. So 20 years later, 40 years later. All right, so using the equation up there, the average is 1 over b minus a, so the bigger number minus the smaller, so 40 minus 20, times the integral from 20 to 40 of f of t dt. So they gave us the function up here. So we've got, 1 over 40 minus 20, make sure you use parentheses like that. So that's 1 over 20. Times the integral from 20 to 40 of that function. So 570 times 1.037 to the t power dt. Okay, so you'll plug this into your calculator as I showed you before. You're going to hit the math button, option 9 fn int, punch this in as exactly how you see it right here, with the t and all that as the exponent, with the limits of integration from 20 to 40. So you should get, 1 over 20, so on your calculator you should get 34,646.2. So then take that number, divide by 20, and you should get 1732.81, and the units are thousands of people. Okay, and there you go. And let's see, so that's the end of this chapter. Thank you very much.